Hello everyone. In this video, we are going to see single-phase semiconverter with RL load. The single-phase semiconverter is a one-quadrant converter. The converter can operate only in one quadrant. The circuit of the single-phase semiconverter with RL load is given here, which consists of two thyristors and two diodes. The devices are numbered as T1, 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 T2, and D2. The output voltage is measured across the RL load V0, and the output current is given here, and this is the source current. The converter can operate in two modes of operation: continuous conduction mode and discontinuous conduction mode. Since this is going to be one quadrant converter, we will be able to get only the rectification mode of operation. So we will not be able to get the inversion mode of operation. So why it is called as single quadrant converter. Now we will see the modes of operation. First, let us see continuous conduction mode. So in continuous conduction mode, the output current I0, it is always greater than 0. So at the time of triggering the SCR, the output current will be greater than 0. So what the main thing which we should understand in single-phase semiconverter is that the semiconverter will have the inherent freewheeling action. That is, we need it is not necessary to connect a freewheeling diode across the load in case of semiconverter. So this is going to have the single-phase semiconverter. The semiconverter will have inherent freewheeling action. So it doesn't require any separate freewheeling diode to be connected across the load. So we can divide the operation into different intervals. At alpha, we will trigger T1. So once the T1 is triggered, from alpha to pi, the devices T1 and D1 will be in on condition. Therefore, the output voltage V0 will follow the input voltage Vs. Then, since load current is continuous, I0 will still flow. I0 will not reach 0. So it will be always greater than 0. So which means that the thyristor T1 which was triggered, it will not be turned off at pi, because since the load current is greater than 0, it is not 0, the T1 will continue to conduct. So what happens is the freewheeling path, the I0 will be flowing through the freewheeling path formed by this T1 and D2. Since the load current it is not 0 now, the T1 will continue to carry the load current along with the D2. So this T1 and D2 combination will now serve as the freewheeling path for the load current. So the load current will now flow through this T1 and D2, constituting the freewheeling mode. So the output voltage during T1 and T2 or in the on condition will be equal to 0. So from pi to pi plus alpha, we have the freewheeling mode. Okay, so we have the freewheeling mode. The load current is carried by T1 and T2. So hence, V0 will be equal to 0. Now at pi plus alpha, we are triggering at pi plus alpha, T1 is turned on, T2 is turned on. So once the T2 is turned on at pi plus alpha, from pi plus alpha to 2 pi, we have the conduction of T2 and T2. Hence, V0 will be equal to minus Vs. And from pi to 2 pi plus alpha, T2, again, we have the freewheeling mode, that is freewheeling interval. So T2 and T1 will be in on condition, constituting the freewheeling path for the load current. So V0 will again be equal to 0. So this is the case for V0. Hence, we can draw the output waveforms. So, we'll draw the waveform now. First, we will draw Vs. We will draw the waveform for one cycle. So this is Vm. This is minus Vm. Now we can draw the gate signals for T1 and T2. At alpha, we are releasing gate pulse to T1, and at pi plus alpha, we are releasing gate pulse to T2. Now we will draw the output voltage waveform. So output voltage will be, we will draw the waveform starting from alpha to pi when T1 and D1 are in on condition. The output voltage will be same as the input voltage Vs, and from pi to pi plus alpha, we have T1 and T2 conducting, which is nothing but the freewheeling interval, and that time the output voltage is 0. Then from pi plus alpha to pi, we have T2 and T2 conducting. So output voltage will be equal to minus input voltage minus Vs So this voltage, the input voltage, will now appear as the appear in the positive side. So this is the from 0 to alpha, we will have the freewheeling interval. The devices which are conducting will be T2 and T1. So this is the output voltage waveform. Now we can draw the output current I0. The output current I0 is continuous current. So at the time of triggering, the output current will start from a value greater than 0, and at pi plus alpha, it reaches the same value, and then again the current will start increasing. And this is going to be the current waveform. The input current waveform, if we draw the input current waveform, that is source current waveform. The source current waveform will be same as the output current waveform from alpha, that is whenever T1 and T1 are in the on condition, the input current will be positive. So the input current will be same as I naught whenever T1 and T1 are in the on condition. So input current will be same as the output current. The input current will be same as the output current during T1 and T1 conducting. This current will be carried by T1 and T1. And during the freewheeling mode, the input current will be 0. Then from pi plus alpha to pi, the input current will be minus Vs, minus I naught. Okay, so this current was carried by T2 and T2. So during the freewheeling action, that is during the conduction of T2 and T1, we will not have any supply current because the source is now disconnected from the load. The load current freewheels through the freewheeling devices, such as in the freewheeling mode, the load current is being carried by either T1 and T2 or T2 and T1. So these are all the waveforms for the single phase semiconverter with RLO. Now we can derive the V0 average. We can see here that the output voltage waveform is same as that of the output voltage waveform of the single phase semiconverter with R load. So the waveform shape of the waveform, it is similar to that of the output voltage waveform of the single phase semiconverter. So same V0 average and V0 RMS we will get. So we can have the derivation V0 average, which will be equal to 2 by integration from alpha to pi V0 d omega t, because from pi plus alpha to from pi to pi plus alpha, V0 is 0. So I have not considered that interval, which will be equal to 1 by pi integration alpha to pi Vm sin omega t d omega t, which is equal to 1 by pi Vm we can take outside minus cos omega t alpha to pi, which is equal to Vm by pi. Substituting the limits, we will get minus cos pi plus cos alpha, which is equal to Vm by pi 1 plus cos alpha. So the V0 average depends on the value of cos alpha. For alpha equal to 0, we will get V0 average equal to 2 Vm by pi. And for alpha equal to 180 degree, we will get V0 average equal to 0. So now we can derive the V0 RMS. V0 RMS will be square root of 1 by pi. So actually 2 by 2 pi, 2 gets cancelled out. So 1 by pi integration from alpha to pi V0 square, that is Vm square sin square omega t d omega t whole to the power 1 by 2, which is equal to 1 by pi. We can take Vm square outside. Integration alpha to pi 1 minus cos 2 omega t by 2 d omega t whole to the power 1 by 2, which can be written as Vm by 2 can be taken outside. So root of 2 pi integration of 1 will be omega t minus cos sin 2 integration of cos to omega t will be sine to omega t by 2, integrate limits varying from alpha to pi whole to the power 1 by 2. So which will be equal to Vm by root 2 pi. After substituting the limits, we will get pi minus alpha minus sine 2 pi by 2 plus sine 2 alpha by 2 to the power 1 by 2. So which will be equal to Vm by root of 2 pi minus alpha plus sine 2 alpha by 2 whole to the power 1 by 2, because sine 2 pi by 2, sine 2 pi is 0. So that term will not appear here. So, so far we have seen the single phase semiconverter with RL load in continuous conduction mode, wherein the load current is always positive, which is greater than 0. And so, we have also derived the V0 average and V0 RMS values. The value of V0 average and V0 RMS will be same as that of the single phase semiconverter with R load, because the output voltage waveform remains the same. Now we are going to see discontinuous conduction mode. In discontinuous conduction mode, the output current I0 will be 0 for some time. So the different intervals for discontinuous conduction mode will be from alpha. At alpha, when we trigger T1 and T1 will conduct from alpha to pi. So from alpha to pi, T1 will conduct along with T1, making V0 equal to Vs. Then from pi to pi plus alpha, from pi to, since we have discontinuous conduction mode, the current will reach 0. I0 will reach 0 at angle called beta, where beta is extinction angle. So from pi to beta, we will have the freewheeling action taking place, and the current will be flowing through the freewheeling path formed by T1 and T2. Hence, during that time, V0 will be 0. And from beta to pi plus alpha, T1 will be turned off, and T2 is triggered only at pi plus alpha, so no device will be on. Hence, V0 will be 0. At the pi plus alpha, when we trigger T2, from pi plus alpha to 2 pi, T2 and T2 combination will conduct. So, V0 will follow minus Vs. From 2 pi to pi plus beta, we will have freewheeling action taking place due to the conduction of T2 and T1. So T2 and T1 will provide a freewheeling path for the current, and so the V0 will be 0. Then from pi plus beta, from pi plus beta to 2 pi plus alpha, no device is on. So no device is on. No device will be in on condition. Hence, V0 will be 0. So if we see the V0 voltage, V0 waveform if we see the V0 will be equal to Vs from alpha to pi. Then from pi to pi plus alpha, V0 is 0. Again, from pi plus alpha to from pi plus alpha to 2 pi, V0 is minus Vs. Then from 2 pi to 2 pi plus alpha, V0 is 0. So hence the V0 waveform will be same as that of the continuous conduction mode waveform, V0 for obtained for continuous conduction mode. But the current waveform will be different. So we will draw the current waveform alone. I0 your current waveform will start from alpha and it reaches 0 at beta. This current waveform will the current will be carried by from alpha to pi, the current will be carried by T1 and T1, and from pi to beta, the current will be carried by T1 and T2. Then from beta to pi plus alpha, no device is in the on condition, so current will be 0. So from alpha to pi, we will have the main devices conducting T1 and T1. From pi to beta, we will have the freewheeling action taking place. Then from pi plus alpha to pi plus beta. This is pi plus beta. From pi plus alpha to 2 pi, current is carried by T2 and T2 combination. From 2 pi to pi plus beta, current is carried by T2 and T1, that is freewheeling mode. Then from pi plus beta to 2 pi plus alpha, we will have the current equal to 0 because no device is in the on condition. Similarly, before alpha, we will have a current which is carried by T2 and T1 freewheeling action formed by freewheeling path. T2 and T1 combination will carry the current. So from this point to this point, no device is on, so current is equal to 0. This is I0. Now we can draw the source current waveform. The source current waveform will be will be equal to I0 from alpha to pi and is equal to minus I0 from pi plus alpha to 2 pi. From pi plus alpha to 2 pi. So source current will be same as I0 when T1 and T1 are in on condition and is equal to minus V0 minus I0 when T2 and T2 are in the on condition. Okay, so this is the IS, that is input current IS. So IS will be equal to I0 value when T1 and T1 combination are in on condition and is equal to minus I0 when T2 and T2 are in on condition. The V0 average and the V0 RMS both are same as that of the V0 average and V0 RMS found in the continuous conduction mode, since V0 waveform is same. Since V0 waveform is same, there is no change in the V0 waveform. So V0 average and V0 RMS both are same as we found for continuous conduction mode. Thank you.